document camera here with my phone. So I really like writing in person. But if for some reason my paper goes out of view for what I'm writing, feel free to interrupt me, and also feel free to interrupt me with questions. Yeah, because I planned a 40-minute talk, not an hour-long talk. So this should be fun. So thank you all for coming. I'm so excited to get to hear from all of you. A little disappointed I don't get to see more of your faces today, but maybe this will be remedied soon. Yeah, so this is joint work with Roman Bezrkovnikov and Simone Riche. So I'll tell you some background for this story. So the setup is that we start with a pair of connected reductive algebraic groups that are Langlands dual to each other. And the guiding insight for what I'm going to discuss is that the affine Hecke algebra I'll call this F, admits both G and G check categorifications. Okay, so I'll discuss those briefly. The affine Hecke algebra that I'm talking about is the one corresponding to the extended affine file group, which is given by the finite file group. Should go the other way. And the weight lattice or co-weight lattice. So this is the co-weight lattice. In my setup, this is the co-weight lattice for G, or the weight lattice for G check. And so the way these manifestations work is that on the G side, we use constructible sheaves. So we take the affine flag variety. So this is G evaluated over Laurent series modulo an Iwahori subgroup. And then we consider a category with lots of adjectives. So I want to take Iwahori equivariant, and I also want to impose mixed. So this is the mixed I equivariant, constructible K sheaves on the affine flag variety. Here, I'll front off the page. And the multiplication in this algebra comes from convolution. And this is due to Iwahori Matsumoto a long time ago. Maybe not so long in the grand scheme of things. And then on the G check side, we use coherent sheaves. And for this, I want to use the Steinberg variety. So this can be realized as the set of triples, let's say X and a B1 and a B2. So X, I want this to be nilpotent in the Lie algebra associated to G check, and then B1 and B2 are Borel's. And I want this incidence condition to hold. And of course, if I take the nilpotent and one of my Borel's, then this looks like the Springer resolution. So this can also be realized as a fibered product of the Springer resolution with itself over the nilpotent cone. And then I take coherent sheaves. I want them to be G cross GM equivariant on the Steinberg. And then this also has a type of convolution. All right, and so this is due to Kazhdan and Lustig. And maybe I should also mention Ginsburg. At least this is carefully written down when we're dealing with the
So you're off the bottom of the screen now, I think.
Sorry, thanks. Okay. So yeah, I want to emphasize that we really do like both of these categorifications. So for one thing, if I'm looking at constructible sheaves, then here it's easier to see the Kazhdan-Lustig basis, for instance, because this just corresponds to the intersection cohomology sheaves. On the other hand, if I'm looking at coherent sheaves, then it's easier to see what is known as the Bernstein Presentation. And so to see this, you're kind of regarding the Steinberg variety in two ways. So I can get line bundles from a copy of the flag variety. And then I can also parameterize the irreducible components by the finite file group. Should put a number here. This finite file group. Just by lifting G orbits from two copies of G mod B and then taking the closure of those. So those are my irreducible components. And then the big theorem is that what you think is two categorifications is really one categorification. They just look different. So the two categories are equivalent as monoidal categories, at least if I'm working in characteristic 0. Somebody's calling. Okay, so the hope is to prove this for a positive characteristic. At least if this characteristic is large enough. All right. Okay. Right. So next I'll tell you some progress. All right, so I need to tell you two categories. So on the G side, we're working with constructible sheaves. And so here we start with the category of perverse sheaves on the affine flag variety. in the unmixed setting. And then I need to define a quotient. Sorry, I have to apologize. I'm currently visiting family because we had a death in the family last week. So I'm not in my usual situation. So, all right. So the quotient that we're taking is by the Sayre subcategory generated by VICs. And I want to quotient out by all of those who have a label whose length is positive. And so if you know much about the affine vowel group, you'll say, well, that doesn't leave very much left. And that's exactly the point. So this is a pretty big chunk of the category that we're removing. So of course, this is an abelian category. I'm taking a Sayre quotient. But it also has a monoidal structure. So let's call this star, but with a little 0 here. So the definition of this monoidal structure is I take two objects in the quotient. And so I can take lifts of them in the category of perverse sheaves and convolve them. And now the convolution on the affine flag variety does not preserve the perverse sheaves. So I have to take the perverse homology of this and then I quotient. So this is my definition of the monoidal structure. And this inherits associativity, but it also is commutative. All right. A second property that you might have already calculated is the number of irreducibles in this category is pretty small. So this is, well, this is going to be given by the skyscraper sheaves. The ICs given with 0-dimensional support. So that's going to be the same as the number of connected components of the affine flag variety. And this is the same as the size of the fundamental group of G. All right, so this is the category that we're dealing with. And so the fact that I have this monoidal structure that's commutative means I want to think of this as a category of representations with its corresponding tensor product. But the problem here in this situation is that there's not an obvious fiber functor. Okay. All right, so now I'll tell you what happens on the other side, the category that we're considering. So on the G-check side, I'm dealing with coherent sheaves. And so I don't want to work with this full category of sheaves on the Steinberg variety. I want to replace it with something that I feel like I understand better. So this category acts by convolution on the category of coherent sheaves on just a single copy of the Springer resolution. And then, so that's my first replacement. And now I want to do something analogous to taking a Sayre quotient here. And so analogous to taking the Sayre quotient is restricting to an open subvariety. All right, so what are we going to take? Take the Springer resolution. Of course, it's a resolution of singularities of the nilpotent cone. Sitting inside here, I have the open dense G orbit called the regular orbit. And because this is a resolution of singularities, it is an isomorphism over this open dense smooth thing. So I have a copy of this orbit sitting inside here. So that's what I want to restrict to. I want to restrict to the regular orbit. So we look at coherent sheaves that are G-check equivariant on the regular orbit, or representations of the centralizer of a regular nilpotent. All right. Yeah, so this is a category of representations. So this is where we want to look. Good. So here's the theorem. I already wrote the names, so I will abbreviate Romans. Yeah, so the theorem, which is progress towards our big hope, is that in fact these two categories are equivalent as monoidal categories, as long as my characteristic isn't too small. So maybe I'll stop for a second. Are there any questions so far?
Where do you get the symmetry from? The fact that this is a symmetric monoidal category?
Well, sort of a naive way to look at it is that if I'm, is that the irreducibles that are left in this quotient are just the skyscraper sheaves, so they commute with each other. So those are the composition factors of whatever's in this category. There are other questions?
Is there like an obvious, I mean, when you're looking at representations on the centralizer, you could restrict to the connected component, right? Or kind of look at the interplay between the connected component. What is the, do you know what goes on the side of the coherent sheaves if you?
So that would just be if you're just talking about looking at the center, I guess. And so for the coherent sheaves, you could, break down the category, decompose it according to the central characters. So that would correspond to the different connected components.
Oh, right. Okay. There's just a decomposition, but okay. You can still just decompose the left-hand side with central characters. Okay. Yeah. Okay. Thanks.
And there's one more question from, sorry.
Is it written somewhere?
Valerio raised his hand, but I can't see it raised anymore, perhaps. Oh, there we go.
Can you hear me, Jordi?
Yep.
Yeah, my question was just, did you say why you were taking those quotients in the first place?
Why I'm taking the quotient in the first place is because I want to understand the original category. And these quotients are somehow easier to deal with in some ways. For instance, they have fewer irreducible objects, but they also remember a lot of information about the category. Yeah, so sort of a quick thing to say, which I was planning to say in a bit, is that I hope to play a game that's similar to Sergal's idea with category O. So he defined this functor V, and this functor V was fully faithful on projectives. So all of your information about projectives got remembered in this other category. And so for Sergal's situation, it was modules for the coinvariant algebra. And in our situation, it turns out that what plays this role is representations of the centralizer of the regular unipotent.
Okay, thank you.
Yeah. Okay. Yeah, so now maybe I'll say a few words about what goes into this. So some ingredients. Yeah, so the first problem that I mentioned was that we don't have a fiber functor. So we need, I should have thought about turning off my notifications. I did not prepare. I didn't think of all the possible problems that could come up. Oops, and now I've messed this up. All right, sorry guys. Let me see if I can go back to my camera. Okay, and now it needs to be swapped there. Okay, good. Yeah, that's my ex-mother-in-law. Hopefully she doesn't say anything horrible, but we're nice people, so I don't think that'll happen. Okay, cool. All right, so ingredients. Yeah, so replacement for the fiber functor. Yeah, so we take representations for the dual group, and this is equivalent via geometric satake to perverse sheaves on the affine Grassmannian that are equivariant with respect to the spherical. And then this has a functor to perverse sheaves on the affine flag variety. And then here's our quotient. And so the functor here is this nearby cycles functor defined by gate squarey. And so this is our replacement for the fiber functor. So we have a category of representations already here that we understand. And so we need to show essentially that the Z bar looks like a restriction functor. Okay. So essentially what this means is any object in P0 can be realized as a subquotient of something from this category of representations. So that's essentially a faithfulness property. Okay, so this allows us to deal with the first issue. So we get representations of some group, and it's a subgroup of the dual group. Okay. All right, so the next thing is to see why is this subgroup related to the centralizer of a regular unipotent. So this comes from the fact that this functor Z, Gates-Gray's functor, there's a separate construction which is slightly different due to Chinwen Zhu. This functor is given by nearby cycles. So the nearby cycles construction comes with an automorphism from the monodromy. And it turns out that this is unipotent. So this gives us a unipotent element in G check, not necessarily regular. So this says that H has to be a subgroup of at least the centralizer. All right, so next, we need to see that this is in fact regular. So for this condition, we have to look at Wakimoto sheaves. So you find an extension of Wakimoto sheaves. How do I want to say this? You find an extension of Wakimoto sheaves that corresponds to a filtration of, okay, so the representation I want to look at is the induced representation from a fundamental weight, where this fundamental weight is corresponding to the simple root I'm looking at. And so to get that this is regular, I need to get that the component of the Borel that corresponds to the simple root is acts non-trivially. So this V, I look at this representation. This has a weight filtration. And what happens when I'm looking at the sheaves on the affine flag variety, this corresponds to a perverse sheaf, which is the image of this under Gates-Gray's functor. And so the weight filtration here corresponds to a filtration by Wakimoto sheaves. So essentially what you can do is you can say that this action has to correspond to an endomorphism. This endomorphism comes from this non-split extension of Wakimoto sheaves. And because this extension is non-split, that forces this to be a non-trivial action. So non-split extension forces non-trivial action of component in, let's say, B check on this object. All right. So this is just a bit technical. Okay, and good. So now we have H is a subgroup of the centralizer of a regular unipotent, but it's not clear that it's the full thing. So the final step is we need equality here. Okay, so for this is an interesting fact, I think. So I'm mentioning it for those of you who care about the weeds of representation theory. So we have the following lemma. If I have a group that sits inside the centralizer of the regular unipotent, and it contains the full center of my group, and for every tilting representation, I have the following property. So the property that I want to look at is the invariance. So I compute the invariance with respect to the centralizer. I compute the invariance with respect to the subgroup. And of course, there's an inclusion here. And the condition that I want is that, in fact, this is equality. So if this holds for every tilting object, then this forces the subgroup to be the full centralizer. Okay, so then we need to show that this property holds for our group. So we have to do some computations. So the first thing that you show, this should be familiar to some of you in the setting of groups in characteristic 0. This should be a U. If I take the dimension of these invariants, then this is the same as the dimension of the 0 weight space. So that's pretty cool. And then the dimension of the 0 weight space, remember I told you that if I'm looking at perverse sheaves on the affine flag variety, and I take a central sheaf, something in the image of Gates-Gray's functor, then the weight filtration for the representation corresponds to a Wakimoto filtration. So this means I can actually compute the 0 weight space looking at sheaves on the affine flag variety. But I'm not going to work in that category. We have to use a replacement for it, which makes everything complicated if I'm going to tell you all the details. So the replacement is, instead of the I equivariant sheaves on the affine flag variety, I have to work with Iwahori-Whittaker sheaves on the affine flag variety. Yeah, so I don't want to say much about that, but if there's time left over, maybe someone can ask me a question about it. So this object right here, this is not the skyscraper sheaf, but it's the smallest perverse sheaf on the affine flag variety and the identity component. So that's what that is. And then I take the image of the central sheaf corresponding to V. So this computes for me the dimension of the 0 weight space. And then of course, here's where the circle style argument comes in. If this V is tilting, then this dimension of the HOM remains the same when we go to our quotient category. Maybe I'll say this is the image of the skyscraper here, and then this is what we call Z bar of V. And of course, we know this is a category of representations now. This is representations of H, so this is the invariance under H. All right, good. So that's yeah. So that's the proof of the theorem, the first step. So this is what's been done so far. And yeah, as I mentioned before, the hope is to upgrade the above equivalence to be able to prove a positive characteristic version of Bez's theorem, relating our two categorifications, by using some circle style arguments. So in circle situation, he was trying to understand the principal block of category O in terms of perverse sheaves on the flag variety. And we understood how to go from category O to D modules. But I think I've never heard this from him, but I made this up in my head, just knowing what I know about circle. I think he was deeply unsatisfied that he had to go through D modules before he could get to perverse sheaves. So he wanted somehow to relate these categories directly because, in his mind, that would have been a more beautiful way to go about this. And so he ended up coming up with this, this functor V to take you to the covariant algebra, to the Weil group. And I think the most obvious way to get from perverse sheaves here is to take cohomology. And this is not analogous to our situation. This is causal dual to our situation. So what Sergel came up with instead was like, oh, this looks like causal duality, which is not what we want. Instead, we want a quotient to be more analogous to our situation. Okay. Yeah. So I think that's all I prepared to say. So maybe I'll stop here and see if people have some questions.
May I?
Yes, go ahead.
So I remember Roma Bezrukavnikov given talks where this kind of result, the final result, was a theorem. Maybe you could comment on that.
Well, I'm sure in his mind it is a theorem, but it's not written down. So that's my comment about that.
Okay, that's a good comment. Thank you.
Any other questions? Oh, Tony.
Yeah, thanks. So just wanted to understand the relation to Roman's theorem. Like, would this be a new proof, even in characteristic 0, or?
It is a different proof in characteristic 0. Well, maybe I'll just be honest and say I don't really understand his proof in characteristic 0. But a step along the way is understanding the anti-spherical module. And certainly we're going about understanding the anti-spherical module in a very different way.
And just trying to understand how one would guess like the statement of your theorem. Like, can you formally deduce your theorem in characteristic 0 from Roman's theorem?
Yeah. You mean the understanding the representations of the centralizer in terms of this quotient? Yeah. So that can be deduced from the equivalence.
Is that like hard to see, or is it something that you can say quickly?
So it's easier to see if instead of working with all sheaves on the affine flag variety and coherent sheaves on the Steinberg, I just look at coherent sheaves on the Springer resolution, which corresponds to the anti-spherical module for the Hecke algebra. And so that is equivalent to this Iwahori-Whittaker thing that I mentioned very briefly before. Yeah, so I think it follows pretty quickly from having that equivalence with, yeah, between the anti-spherical module in terms of the affine flag variety and then the version in terms of coherent sheaves on the Steinberg variety.
Okay, thanks.
May I make a comment?
Yes, yes. Please.
So Roma's theorem has two parts, and maybe this comment can be converted to a question. So there is a question, there is a part about derived equivalence, but there is also a part which describes what happens with T structures. And back to Tony's question, if you know both parts, then this resulting characteristic zero will be an easy consequence. After all, the theorem that Laura proved is about equivalence of abelian categories.
Yes.
So now, a question. So how about the abelian equivalence part? Is it supposed to hold, and kind of what needs to be modified?
So if I'm uncomfortable with this question for the affine Hecke category, because of course I know what perverse sheaves mean, but I feel like I don't have any intuition for what the corresponding T structure should be on coherent sheaves on the Steinberg variety. But if I make the replacement of working with the Springer resolution, then yes, this equivalence between derived category coherent sheaves on the Springer resolution and this Iwahori-Whittaker sheaves on the flag variety, that preserves there's a natural T structure that you can define on the coherent side that matches with the perverse T structure there. And I can't remember what your question was.
I mean, it was somewhat loose question, but somehow I thought that you are supposed to have some statement which, let's see. So you start with the T structure of Harish-Chandra bimodules.
Mm-hmm.
And then this is not supposed to be equivalent to the perverse T structure, but you need to take perverse Harish-Chandra bimodules.
Mm-hmm.
So then in characteristic zero, well, in characteristic zero, you don't deal with Harish-Chandra bimodules, you deal with Rukavnikov and with Springer.
Mm-hmm.
But then if you're in characteristic P, you can deal with actual Harish-Chandra bimodules over the universal enveloping algebra.
Mm-hmm.
And so there's supposed to be, well, I mean, at least one could hope to have an equivalence of this kind.
Yeah, I'm not sure if I can say anything about that.
Okay.
Can I ask a question? I'm sorry, I can't message or raise my hand. Is there is the analog of that functor you construct, has it been studied or been defined directly in terms of Serge bimodules or their characteristic P version? So purely algebraically?
Which functor do you mean? The
So the functor you could be going, I mean, either of the two, the one going from your original category to the quotient category, say P to P0 or the derived versions.
Yeah, so there's if I take this quotient by this quotient functor, then this has been studied before. So just on a finite dimensional flag variety. And so this, yeah, so already for the finite dimensional flag variety, you can talk about some tilting objects and end up getting a fully faithful on tilting objects property.
So my question is really about the affine flag variety case, okay?
Yeah.
In that case, is that also studied?
people understood that exactly the same arguments would apply. As far as like when you construct this quotient and show that it's fully faithful on tilting objects.
Yes, that's my question.
Yeah, it's the exact same argument for the finite dimensional flag variety as it is for the affine flag variety. The problem is if you want to translate this into a statement about projectives, then you're in trouble.
Okay, okay, I understand. So there is some algebra that's not done there. Yes. So my question, a second question would be related to a question that was raised at another talk previous week by Ivan Nozef, whether that functor has better properties than say Serger's functor in the G mod B case. What I mean, how good does it behave on say Verma filtered Weil filtered modules or standard shift filtered modules? I mean, is it something that's like the usual case, or is it a bit better?
Yeah, so the statement is that it's fully faithful. The most general statement that I can make is that it's fully faithful if I take, so co-standardly filtered things here and standardly filtered things here. So that's the best you can do.
Okay, so that's better than the so that's very good. That's better than the Serger original finite flag functor.
I think it's the same, isn't it? Like if you apply Ringel duality or something, I think it amounts to the same thing.
Like Serger's functor would take, if you take two different a Verma to a nabla, like where the parameters are different, Serger's functor would map that to a one-dimensional space, so it wouldn't be fully faithful on standard to co-standard.
Yeah, but co-standard to standard.
Also not, I think.
Okay. There's this nice little paper called Tilting Exercises by Balanson, Bezrakovnikov, and Merkovich, where they study this quotient for the finite dimensional flag variety. And they show it has this quotient functor has the property of being of having this fully faithful property. And then they mention like, oh, if I just, maybe it's not Ringel duality, but using one of these auto equivalences of the category, they can transform this functor into Serger's functor V. Maybe it's like convolution with the long word or something. I don't know.
So isn't this statement equivalent to saying that your functor is fully faithful on tiltings?
Yes. I guess it implies it for sure.
Yeah, right. But I mean, it's kind of with some basic homological algebra, one could also
once you have fully faithful,
imagine that you have a implication in the opposite direction.
Yeah, probably.
It's like, you know, co-standards admit tilting resolutions in one direction and standards admit tilting resolutions in the opposite direction.
Yeah.
And then so I think that the answer to Raphael's question is that this situation is just as good as original circle.
But I'm confused. There's been a Ringel duality in I'm confused because is Serger's original functor fully faithful on tiltings?
No, Serger's original functor is fully faithful on projectives.
Yeah, so that's different.
But then I can take an auto equivalence of this category that switches projectives with tiltings. And so then I get a different functor that's fully faithful on tiltings. And so in our situation, we can't, you know, take an auto equivalence to go back to projectives without leaving our category or doing something more extreme. So we have to work with tiltings directly, but that's okay. We like them.
This is a little bit of a side question, but is there a version of derived Satake equivalence in characteristic P?
Yes. Do you mean so derived Satake?
Yeah, maybe considering derived loops in G or BG.
Yeah. So there's a sort of version of understanding the mixed category in characteristic P. But if I remove the word mixed, then I think the answer is no. There's not a derived Satake.
Mm-hmm. And with this mixed version, what does it compare with?
Yeah, so by mixed version, I mean there's one way to define mixed sheaves in positive characteristic by using parity sheaves. So parity sheaves are exactly analogous to pure sheaves in the fact that when you push and pull, if I push along a proper even map, and pull along a smooth map, then these parity sheaves are preserved. So they're analogous to the pure sheaves that you would use in characteristic 0. And so there's if I look at parity sheaves on the affine Grassmannian, then I can relate these to, if I'm in the underived setting, to tilting representations of the dual group. This is Shuto, Mautner, and Williamson. But if I'm looking at their higher degree X in the derived category, then I also need the derived category of coherent sheaves on the nilpotent cone.
So in the end, it's an equivalence with derived category of coherent sheaves and nilpotent cone, which is
it's not quite an equivalence, because the derived category of sheaves on the nilpotent cone is not equivalent. Yeah, you can't write everything as a bounded complex of tiltings. So it's not quite equivalence.
But there is a fully faithful embedding or something like this. Thank you.
Yeah, you're welcome. Thanks for the question.
Any other questions? Well, if not, let's thank the speaker again.